Okay, so let's do this. Let's look at Newton's second law in spherical coordinates. I already made a video about Newton's second law in polar coordinates, so I'm now going to do the same thing in spherical coordinates. I will tell you, it's a little bit more complicated. I'd rather write this out on paper, but it's just too complicated to do that. So hold on to this. And I even may make a mistake, because that's me, Okay, so let's start off with Newton's second law in Cartesian coordinates, because just to make sure we understand what's going on there. So imagine that I have some particle right here, some particle r at vector position r, and I want to do Newton's second law. Well, Newton's second law says that the net force in that particle is equal to the mass times the acceleration, and the acceleration is the second derivative of the position vector. Force is a vector. Okay, so let's take the derivative of the position vector. The position vector in Cartesian coordinates is some x value in the x direction plus some y value in the y direction plus some z value in the z direction. So that's where that x hat, y hat, z hat come from. Now, a lot of times we'll call it I hat, j hat, k hat, or we won't write it at all. We'll just write it as a thing. It's so easy that we just take it for granted. Okay, so let's take the derivative of r twice. So the one thing that we use, this is for classical mechanics, the one thing that we use a lot is this idea, this notation of dot notation. So in dot notation, if you take the derivative of some variable with respect to time, we'll write that as that variable with a dot over it. The second derivative would be two dots. So x dot is the same as dx dt. It just makes things a lot easier. Trust me, things are going to get complicated enough as it is. We need this kind of simplification to make our lives look pretty. Okay, so let's take the derivative. So if I take the derivative of the position vector r, I get the derivative of x with respect to time. I'm taking the derivative with respect to time. The derivative of x with respect to time times x hat, which is x dot, plus y dot plus z dot. I don't think that's that bad, right? That's not that complicated. But we have a product rule. We have x times x hat. So I actually have to take the derivative of x times x hat, which I did. And then I have to take the derivative of x times the derivative of x hat. And so I get these other parts of the derivative there. But in Cartesian coordinates, the unit vectors x hat, y hat, z hat do not change. They don't, no matter where you're at, they're always in the same direction. So these don't change with time, so they're zero. And so I'm just doing that explicitly because it's not always going to be clear in the future. It's not the same in the future. So then if we take the derivative again, the same thing happens, and I get the derivative of r. The second derivative is x double dot x hat plus y double dot y hat plus z double dot z, and everyone's happy. It's cool. Okay, so now let's go to spherical coordinates. So I have a picture of spherical coordinates. Going to draw it myself, but Wikipedia has a great picture, and so I just use that. There's the link to the picture. This is how we define things in spherical coordinates. So here is some point. Instead of defining it in terms of x, y, and z, we have three variables. We have the distance from the origin, which is the variable r, and then we have, if you draw a line from the origin to that point and you measure the angle to the z-axis, we call that theta. And then if you project that down into the xy plane, and I'm not going into all the spherical coordinates, I assume that you've seen this before. If you're looking up Newton's second law in spherical coordinates, I assume you're like, yeah, I know spherical coordinates, okay. So, and then the projection out in the xy plane, this is the angle phi. Some people call that phi. If you want to call that phi, I always call it phi. I don't know why, and I mean, can't we all just get along? And that's spherical coordinates, r, theta, phi. But wait, you could also do it this way, and some people do, okay? So, personally, the difference here is that in this case, the angle in the xy plane is theta, and the angle from the z-axis is phi. So they'll switch those two angles. There's another third version, which they use the variable rho instead of r. From what I understand and from Wikipedia says, this method right here, the second method, is more common in math, and this is more common in physics. I don't know why there's a difference. And in fact, when I was an undergraduate, I did more spherical coordinate problems in math than I did in physics, because you think about the hydrogen atom, we use spherical coordinates. There's the two body problem. You can smash that into two dimensions. So we never really are forced to, and not a whole bunch of problems where you're forced to use spherical coordinates in undergraduate physics. So my experience was with the math part. So I think of it this way. But today, because I care about you, and this is physics, I'm doing it this way. So I'm measuring the angle from the z-axis is theta, not phi. Now, let's just talk about this really quick. Why? Why would you want to do Newton's second law in spherical coordinates? Well, it's the same thing as why you'd want to do it in polar coordinates. Imagine that I have something constrained on the surface of a sphere. In that case, this r value is constant. So I can deal, it's much easier to deal with a constant single variable than to say x squared plus y squared plus z squared is a constant. That's the equation of the sphere, I think, in Cartesian coordinates. So anything that's spherically symmetrical, it might be easier to move to spherical coordinates. Okay, so here's the one animation I made in Python. It's not very good. I was trying to draw my xy axis. So that's the cyan thing is my xy plane. There's my vector. It's a sphere. And I was trying to show these angles, and then that's why I switched over to the image from Wikipedia, which is just better. Okay, so why is there a problem? Well, the problem is that if this is my spherical coordinates, r, theta, and phi, and I want to write a vector in spherical coordinates, I need to have unit vectors in the direction of r hat, of r, theta, and phi. So the first thing is we have this, instead of x hat, y hat, z hat, I have r hat. R hat is a unit vector in the direction of r. Just like x times x hat makes that a vector, right? Because I need to turn my vector r, my quantity r into a vector. I need those x hat values. R hat is a unit vector in the direction of increasing r. So it's pointing that way. And then I have theta hat in the direction of increasing theta, and phi hat in the direction of increasing phi. And this is an orthogonal system. R hat, theta hat, phi hat are all perpendicular, so that's really good. But you'll notice that as this moves around to different locations, these are not constant, right? R hat could be in the z direction. R hat could be in the x direction. It could be anywhere. It depends on where you're at. These are not constant unit vectors, and that's the problem. So suppose we write our position vector in spherical coordinates. Well, if I want to describe this in spherical coordinates, I have the distance from the origin, r, and I need to make a direction. Well, the direction is in the r direction, so it's just r hat. That's an easy vector to write. But now I want to find the velocity, so I'm going to take the derivative of that. Okay, again, I have to take the derivative of the r, that's r dot, times r hat. Plus, because of the product rule, I have to take r times the derivative of r hat with respect to time. So that's r dr hat dt. I didn't write that r dot because it just gets a little r dot, r hat dot. I just don't like it. You can write it if you want. I don't like it. I don't like two hats, two decorations. But the question is, what is dr hat dt? We don't know. I mean, we know, but we're going to find that out. So we need to figure out dr hat dt. And so I think the important thing here is the problem is that these unit vector derivatives are not zero with respect to time, and we have to figure out what they are. So the easiest way to do this is to switch back to Cartesian coordinates. Because in Cartesian coordinates, I know the derivatives of the unit vectors are zero. So here is my relationship between Cartesian and spherical coordinates. What I want to do is write r is x hat plus y hat plus z hat, but I'm going to write x in terms of r and theta and phi. So this is the normal conversion to Cartesian coordinates. If you know r, theta, and phi, then y hat. And so this is just the projection. Sine theta is the projection into the xy plane, and then cosine phi is a projection on the x-axis, and same thing for y, and then z is just a projection onto the z-axis. And so those are my conversions. And so now I can write my r vector as this, right? So here's my x, that's x hats, because that's x, y hat, and z hat. But I didn't write it in terms of x, y, and z. I wrote it in terms of r, theta, and phi. Good? Good. Okay. So now I want to find r hat in terms of x hat, y hat, z hat. Because if I write r hat in terms of x hat, y hat, z hat, I can take the derivative because I know the derivatives of the Cartesian unit vectors are zero. They don't change. So here's how we find, you could I mean, a lot of times people just say, oh, I think it's just r, it's just this thing, right? But it's better to figure it out in a certain way. So r hat tells me the direction r changes. So this partial of the vector r with respect to r tells me the direction r changes with r. And I have two r's, right? I have the vector r, and then I have the coordinate r. So one doesn't have an arrow over it. I know, it's not fun, but that's fine. You'll be fine. But then I have to normalize it, right? Because unit vectors have to be normalized. They have to have a unit of value magnitude of 1. So I'm going to take the partial of r with respect to r and then normalize it by dividing by the magnitude of the partial of r with respect to r. Got it. Okay, so let's take the partial of r with respect to r. It's not too bad because, look, here's my first term. There's only one r, so the partial of this with respect to r is just going to be sine theta cosine phi. And the same thing here, sine theta sine phi, and then cosine phi. So I get the partial of r with respect to r is this thing. Now I need to find the magnitude of that. So and I know my little magnitude things are a little short because I was too lazy to fix it. So the magnitude of a vector is just the x component squared plus the y component squared plus the z component squared square rooted. So I just square all these and add them together, and that's what I get down here. That squared, that squared, that squared. Now right here, I can factor out a sine squared theta. So I have sine squared theta, and I'm left with cosine squared phi plus sine squared phi. But cosine squared phi, I'm going to turn off this. Good thing I've noticed it. Okay, I'm going to turn it back on. I do like to see myself because it makes me happy. So that's going to be 1 because cosine squared phi plus sine squared phi is 1. That's in trig identity. And now we're left with sine squared theta plus cosine squared theta, which is also 1. So I get 1. So now I divide this by 1, and so that means that this is my unit vector r hat in Cartesian coordinates. So that's kind of an important idea. Now let's do it again. So let's start up here. Here, I'm going to turn back my camera on. Let's see if I don't know how many of these things. There's a lot of stuff going on here, okay? So I'm going to have to turn off my face because I take up too much space in these things. Okay, let's do phi-hat. So again, it's the same thing. It's what's the direction, how does r change with phi? So partial of r with respect to phi, and then I need to normalize it by dividing by the magnitude of that. So here's my vector r. I'm just going to take the partial of this with respect to phi, and it's a partial, so I'm assuming all the other variables are constant. The partial of this with respect to phi, and there's no phi term there. So I get, right here, I have cosine phi. So the partial of cosine phi with respect to phi is going to be negative sine phi. So I get negative r sine theta sine phi. Up here, I have sine phi, so I get cosine phi. And then there's no phi term there, so I get that. So now let's find the magnitude. So I'm going to take this squared plus that squared. So I get the negative sign goes away. R squared sine squared phi squared plus r squared sine theta cosine squared phi. And what I can factor out the r, so they both have an r squared, so I pull that, it comes out of the radical. And then I can factor out a sine squared theta, so I get sine squared phi plus cosine squared phi, which is 1, and then I have the square root of sine squared is just sine, so I get r sine theta. So the magnitude that's r sine theta. That means I need to take this and divide by r sine theta, and I get this. So that's my unit vector phi-hat in Cartesian coordinates. And again, why are we doing that? We're doing that because I can take the derivative of that with respect to time, and I don't have to worry about x hat, y hat because those are constant. Okay, we got one more. And if you think, oh, wow, he's almost done. No, not done. Okay, so here's my r vector again. We're going to take the partial with respect to, we're going to find theta-hat. So the partial of r with respect to theta divided by the magnitude of the partial of r with respect to theta. Okay, so the partial of r with respect to theta, here's a sine theta term, and so the derivative of sine theta with respect to theta is cosine theta, and then the derivative of sine theta right here is cosine theta, and then the derivative of cosine theta is negative sine theta, so I get that. Now we need to find the magnitude, so I have this squared, r squared cosine phi squared, then this squared, r squared cosine squared sine squared phi. Yeah, that's right. And then that squared, r squared sine squared theta. So I can factor out an r. They all have an r squared. I can pull that out front. So that's r right there. Next, there's a cosine squared phi and a cosine squared phi. I can factor that out. And then that gives me cosine squared phi. And then I get a cosine squared phi plus sine squared phi is 1. So I canceled that. I skipped a little step. And then that's also 1, right? Cosine squared theta plus sine squared theta is 1. So I just get r. So the magnitude, that's r. So if I go back up here and divide this by r, I get my unit vector theta hat. And there you go. Cosine theta, cosine phi, x hat, cosine theta, sine phi, y hat, minus sine theta, z hat. Whew. Okay, let's review. So here is my r vector in Cartesian coordinates. So I'm using the Cartesian unit vectors, but I have the position values r, theta, and phi. So it's a hybrid. And then here's my unit vector r hat in Cartesian coordinates. And then I have my unit vector phi hat in Cartesian coordinates, and my unit vector theta hat in Cartesian coordinates. So that's kind of an important thing, right? Because now that I have these unit vectors in Cartesian coordinates, I can take the derivatives of them with respect to time. Because, again, x hat doesn't change. Okay. If you need a break, pause. If you need to, go get a cup of coffee or something like that, this video is going to be here, okay? I'm still going to be here. Okay, so let's go back to velocity. Here we are with the velocity in polar coordinates. It's the derivative of r with respect to time. So I already did this r dot r hat plus r dr hat dt. So now we can actually use my Cartesian value of r hat, and I can actually take the derivative of this with respect to time. That's what I'm going to do. So the derivative of r hat with respect to time is the derivative of all that stuff with respect to time. So let's break it into 3 pieces, right? Because I have a sum. So I have a derivative of sine theta cosine phi x hat with respect to time, plus sine theta sine phi y hat with respect to time, plus cosine theta. See, I already messed up. This is why I made this as a presentation instead of on paper. I prefer doing it on paper, but I know I'd make a mistake. Okay, so this term, let's look at this. So here's a really important thing. If I take the derivative of this with respect to time, there's 3 terms. So I need to take the derivative of sine theta with respect to time. That's going to be cosine theta. But I have to use the chain rule and take the derivative of theta with respect to time. So I get theta dot. So that's why I have I have cosine theta, theta dot, and then I leave these 2 things constant. Next, I'm going to take the derivative of the cosine phi with respect to time. So I get negative sine phi, but then I have to take the derivative of phi with respect to time, so that's phi dot. So that's how I get this term right here. So the derivative of this gives me 2 terms. Actually gives me 3, right? Because I actually have to take the derivative of x hat with respect to time, but that's 0. I know what that is. So I don't have to worry about it. So I have those 2 terms times x hat. Now I do the same thing for this. In the y direction, I have the derivative of sine theta with respect to time. Oh, I didn't do that yet. I just did that one. Okay. So here's the y hat. I should have left the r hat up there. I get these 2 terms. I have to take the derivative of sine theta would be theta dot cosine. Should that be negative? Sine theta. I think that should be negative. I think I left a negative sign off right there. No, it was sine theta. Aha, got it. See, I made a mistake and unmade my mistake. The derivative of sine theta is cosine theta, theta dot, sine phi, and then the derivative of sine phi is phi dot cosine phi, and then the derivative of y hat is 0. And then finally I have to do this last term, cosine z, which is pretty easy. I take the derivative of cosine, I get negative sine. I have to take the derivative of theta, I get theta dot. There you go. Okay. So let's multiply it out and get all the, because I distribute the x hat, y hat, the z hat's already distributed. And what I want to do now is factor out get all the theta dot terms together. So here's a theta dot term, here's a theta dot term, here's a theta dot term. So if I pull those together and factor out the theta dot, I get cosine theta, cosine phi x hat, cosine theta sine phi y hat minus sine theta z hat. Do the same thing with phi dot. I have a phi dot negative sine theta sine phi, a phi dot sine theta cosine phi, so I get that. Now if I look at this term right here, cosine phi, cosine theta, cosine phi, x hat, cosine theta sine phi, y hat minus sine whatever, that is theta hat. We did that already. That's theta hat. That's kind of nice. And then over here, if you look at this, that's phi hat, right? We already did that. That's phi hat. So you kind of have to think about this. It's not obvious how to do that. You kind of say, well, I'm going to factor out, I can get all the theta dot phi hat terms together to see that. So in that case, the derivative of r hat with respect to time is going to be theta dot times theta hat. Oh, I'm sorry, you got to factor out the sine theta too. Negative sine theta. So the negative sine theta, I have to factor out the sine phi. That's, no, sine theta. I'm going to factor out the sine theta. They both have a sine theta. So I get sine theta times phi hat, and then the theta dot. So that's my derivative of r hat with respect to time. So that's kind of cool. I got one of these derivatives. Now, I actually can do the velocity vector. So we already did the velocity again. We have this has two terms in it because we have to take the derivative of r and r hat. And now I do know the derivative of r hat. So I can put the derivative of r hat in right there, and I get r dot r hat plus r times all of that stuff. And then if I just distribute, I get r dot r hat, r theta dot theta hat, plus r phi dot sine theta phi hat. And that's your velocity. That's your velocity in polar coordinates. There's no more Cartesian, right? I took the derivatives using Cartesian coordinates, but then I switched back to spherical coordinates once I knew the answer. Whew. Oh, we're done. No, we're not done. Okay. You might want to take a break because now we're going to do the acceleration. So the acceleration is defined as the derivative of the velocity with respect to time. So I already know the velocity in spherical coordinates. I know that. I just did it. Go back to the last part. Okay. So that means I have to take the derivative of this stuff with respect to time. So I have the derivative of r dot r hat, r theta dot theta hat, plus r phi dot sine theta phi hat. Okay, well, we can take derivatives. So I get the derivative of this term is going to be, with respect to time, is the derivative of r dots, r double dot. The derivative of this, I get two terms. I get r times theta double dot. Did I miss my term? Oh, I did right here. I take the derivative of r with respect to time as r dot theta hat. And then I have to take the derivative of the theta dot term, and I get that theta double dot times r. This term, I'm going to get r dot, right? I take the derivative with respect to r times all that stuff. Now I take the derivative of phi dot. I get this term, r phi dot sine theta. Now I have to take the derivative of this, which is going to be cosine phi, but then I have to take the derivative of the inside, and I get the theta dot. So I get those two terms. I get all these terms. And that's not it. Oh, but wait. You have to take the derivatives of the unit vectors too. So this term has an r dot r hat. I have to take the derivative of r hat times r dot. So I get that term. And then I have this term right here. I have to take the derivative of theta hat. So it's going to be r theta dot times the derivative of theta hat with respect to time. And then I have to take the derivative of phi hat and multiplied by all that stuff. Well, so I already know this one. I just did this, right? The derivative of r hat with respect to time, I know. That's going to be this. I just did it. I promise you, I just did that. Okay. But what about the derivative of theta hat with respect to time? What about the derivative of phi hat with respect to time? We got to do those, okay? And then we can come back and plug it into this equation and get an expression for the acceleration. And remember, that's what we want. F equals ma. We want an expression in terms of spherical coordinates. Okay, so let's start with theta hat. That's my theta hat in terms of Cartesian coordinates. We're going to do the same thing we did before. Theta hat in terms of Cartesian coordinates. Now I can take the derivative of this. So what am I doing right here? Okay, let's just start with this part right here. That's what I did. So the derivative of this with respect to time, I have two terms. So the derivative of theta hat with respect to time, I get the derivative of cosine theta is negative sine theta, theta dot. And then I have to take the derivative of this. So I get the the derivative of cosine phi is going to be negative phi dot times sine phi. So that's how I get the derivative of this gets those two. And then I have to take the derivative of x hat with respect to time, which is 0. Okay. Now for this term, I have cosine phi, the derivative of cosine phi, theta, is going to be negative sine theta, theta dot. And then I have to take the derivative of the second term, which is going to be phi dot times cosine phi. So I get these two terms right here, both multiplied by y hat. And then finally, my z term, that one's not too hard. It's just one term. So I get negative cosine theta, but then I have a theta dot too. Now for a trick. There's a bunch of tricks. If you try to do this just thinking it out, you could get there. But if you know the tricks, it's a little bit simpler. And I don't like tricks. They're for kids, but whatever. Okay, so let's look at these three terms. This times x hat, this times y hat, this times z hat, they all have a negative theta dot, negative theta dot, negative theta dot. So I'm going to group them together and factor out the theta dot. So I have negative theta dot times sine theta cosine phi x hat, sine theta sine phi y hat, cosine theta z hat. Are you still watching this video? Because this is getting really long, and I'm not even done. Okay. But it's got to be done. It's got to be done. Okay, so now for another trick, I can factor out both of these terms have a phi dot cosine theta. So let's factor out phi dot cosine theta right here. So I have phi dot cosine theta. I'm left with negative sine theta, sine phi. And then here I'm left with cosine phi, y hat, and that had x hat. Okay. So this term right here, if you go back to the review, that's r hat. R hat. And this term right here is phi hat. So the partial of theta with respect to time, theta hat with respect to time, is just going to be equal to negative theta dot r hat plus phi dot cosine theta phi hat. We did it. We did that one. We got another one, right? Okay, one more. So we want to take the derivative of phi hat with respect to time. So there's phi hat in Cartesian coordinates. It looks nice. It looks like this one's going to be easier, but it's not. So I take the derivative of that, and it's just I don't know why I put that term in there. Okay, so I have two terms. I have this term. I take the derivative of this with respect to time. I get there's a negative phi dot cosine phi right there, and this one's going to be phi dot negative phi dot sine phi y hat. I can factor out the negative phi dot, but I have this cosine phi x hat plus sine phi y hat, and I don't know what that is. It's not r hat, it's not phi hat, it's not theta hat. So, trick. It's time for a trick. And I don't think I would ever get this if I didn't look it up, but there is a trick. So the trick is to instead calculate sine theta r hat. And you may think, why would you do so? All these tricks, if you look back, you say, oh, now it makes sense, but you never see them the first time. So sine theta times r hat. Well, r hat is this, right? We know that, r hat. All I have to do is multiply by sine theta, and I get sine theta r hat. I just get sine squared theta cosine phi x hat, sine squared theta sine phi y hat, sine theta cosine theta z hat. I get this right here. That's exact. And then I can factor out of this first xy term, x hat y hat term, I can factor out a sine squared theta. So I have sine squared theta times just cosine phi x hat sine phi y hat. And then I have this other term. Okay, let's do another trick. And you think, oh, all right, we did the trick, we should have the answer. No, double trick. Okay, trick number 2 is to calculate cosine theta, theta hat. So I know theta hat is this. I'm just going to multiply by cosine theta. Well, that's pretty easy. Cosine theta, theta hat is just cosine theta times all that. And then if I multiply it out, I get a cosine squared. I'm going to factor out in terms of the x hat, y hat terms of cosine squared theta, and then have cosine phi x hat, sine phi y hat, and then I have that last term, cosine theta, sine theta, z hat. Whew. Okay, now let's add those two tricks together. Let's add, what was it? R sine theta r hat, sine theta r hat plus cosine theta theta hat. Let's just add those together. So I just calculated both those. So here's my sine theta r hat. That's just from the previous slide. Okay. And then here's my cosine theta hat right there. Now, you'll notice something super nice, because one of the things that we had a problem with was that the phi hat did not have a z coordinate in it. And if we do this, the z coordinates, the z components cancel, the z hats cancel, because I have sine theta cosine theta z hat minus cosine theta sine theta, which is the same thing, z hat. So they cancel. Yay. Remember, I don't know why. So then I factor out this term, the cosine phi x hat sine phi y hat is in both of the terms. So I get these two terms added together, sine squared theta plus cosine squared theta, which is 1. And so I just get left with cosine phi x hat plus sine phi y hat. That's what the term I was looking for. And then I get my derivative of phi hat with respect to time, negative phi dot times all that stuff. And all that stuff is sine. See, that's where my trick comes in. This is that. So it's sine theta r hat plus cosine theta theta hat. And then, oh, let me turn off my camera. My mistake there. So that's my derivative of the unit vector phi hat. Okay, I can turn back the camera on because I have it in the next slide. Okay, so this is my review from before. Remember r hat, phi hat, theta hat in terms of Cartesian coordinates. And now I also have the derivatives of the unit vectors. I have the derivative of r hat, theta dot theta hat plus phi dot sine theta phi hat. I have the derivative of theta hat, negative theta dot r hat plus, I'm getting really tired of saying all these dots, I just want you to know, plus phi dot cosine theta phi hat. I imagine that you're going to have to like watch this in slow speed or something like that because there's so much stuff going on, but I don't know what else to tell you. And then the derivative of phi hat with respect to time is negative phi dot sine theta r hat minus phi dot cosine theta theta hat. Okay, so now we can go back to acceleration. We were trying to find the derivative of r in spherical coordinates, and so we had this, right, without taking the derivatives of the unit vectors. And so now I have the derivative of the unit vectors. I have to include those derivatives also. So I need this, which I have, and now I have that, and now I have that. So here's the part without the unit vectors. Let's just add in our unit vector terms. So this one right here is going to be r dot times the derivative of r hat with respect to time. That's that derivative right there. And then I'm going to take this one right here, r theta dot times the derivative of theta hat with respect to time. So r dot theta dot, and then that's my derivative of theta hat with respect to time. And then I have r phi dot sine theta times the derivative of phi with respect to time. So r phi dot sine theta, and there's my derivative of phi hat with respect to time. I mean, that's the answer, but it needs to be in a much better format. So here we have, this is what we have. Okay, so next thing I want to do is I want to gather all the r hat terms together, gather all the theta hats, and gather all the phi hats. So all of these terms have r hat. So this one, I'm multiplying it out, right? This is r theta dot times negative theta dot r hat. That's an r hat term. And same thing over here. You have to multiply it out, but you do get an r hat term. And so if I combine all those together, I get r hat times r double dot r theta dot theta dot. So I get negative r theta dot squared, and then I have r negative r phi dot squared sine squared phi theta right there. I'm going to slip up so many times in between theta and phi. Now let's do the same thing for theta hat term. You notice we have two of those. They're the same thing. Where are they? No, they're not. We do get two of them though. Here's another one down here. Here's r dot times theta dot theta hat. That's a two term. And then over here I have r phi dot sine theta times negative phi dot cosine theta theta hat. That's going to give me a theta hat term too. A theta hat term. So theta hat, I get two of those, right? Two r dot theta dots. And then I have r theta double dot, and then I have minus r phi dot squared sine theta cosine theta. Sine squared cosine theta. Okay, one more, Here are all the terms with phi in them, phi-hat, 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 phi-hat. You'll notice, again, I'm going to get some doubled up terms. Right here, I have r dot times phi dot times sine theta phi-hat. That's the same as that. I'm also going to get r theta dot phi dot cosine theta phi-hat, which is the same as that term. So they both those double up, and I get phi-hat plus r dot sine theta, r dot phi dot sine theta, r phi double dot sine theta, r, that I didn't combine the terms together yet. But when you do combine the terms, did I do that? No. What did I do right here? Okay. Why didn't, this is the same as that. Oh, I'm just saying these combine together. Duh, I already said that. Okay, and those combine together, and I get this. Oh, that's it. That is the acceleration, the second derivative position in spherical coordinates. Oh, we're not done. You thought we were done. No, it's just like an epilogue. Okay, let's go to the epilogue. So let's go back. Remember, we're trying to do Newton's second law in spherical coordinates. So Newton's second law says the net force is mass times acceleration. So imagine that I have some particle with some force, and I'm looking at it in spherical coordinates. So there's some force. Let's just say there's some single force or net force. It doesn't really matter. So I can write that vector f as some component in the r direction plus some component in the theta direction plus some component in the theta and the phi hat direction. So I can do that. I can break it up into components just like I do in Cartesian coordinates. And if I do that, I can actually write the net force in the r direction as the mass times acceleration in the r direction. But the r acceleration is just that r hat component of the spherical acceleration. So that's just that a r hat component right there. But I get one single equation. And this is going to be nice because imagine that r was constant. I'm stuck on a sphere. Then r double dot is 0, and then I get a much simpler expression. The same thing for theta hat. So in theta hat, this is the theta hat acceleration. I just get the theta force is equal to the mass times the theta acceleration. And then the, oops, that's phi. Oh, I can't believe I messed up on the last frickin' slide. What if I just change it? Let's just change this. Let's see. This is phi. Has anyone ever done that? Change a slide right in the middle of the presentation? Okay, I don't want this up here. I can do that. I'm not redoing the video, that's for sure. Right? Okay. A little bit. So, blah, blah. Let's see. I go down here. Blah, 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 blah. There, I fixed it. Ha. I had it right up there. Okay. So there you go. Newton's second law in spherical coordinates. That took 38 minutes. Just imagine if I tried to do that on paper. I like doing things on paper, but I know I'd have made a mistake and had to redo the whole video over again. So I hope you guys like this because, I mean, this took a long time. This took me like 3 days to put together all these equations, and I still might have made a mistake. I don't think I did. I know that's the right answer right there. So if I did make a mistake, I double made a mistake. I really just don't want to end the video now because I've gone on for so long. So if you've made it this far, congratulations. And congratulations to me. Let's both give ourselves a double high five. That's a double high five. Okay. I'll talk to you guys later.